Alright, so for this particular video, we have an object of mass m. Little m is tied to one end of the string. It moves in a circle with a constant speed v on a horizontal frictionless table. The second end of the string is connected to a bigger mass m and goes through a small hole in the table. And it wants us to find the value of big M, which is the hanging block here, in order for the system to stay in equilibrium. So here are your choices: A, B, C, D, and E. So all right, let's go ahead and do it. So before we attack this, I'm going to go ahead and draw out my velocity or my speed here. It says constant speed. So I don't know if the diagram is going clockwise or counterclockwise. It doesn't really matter. I'm just going to draw my arrows here going counterclockwise. So I'm just going to draw that V. So if you want, you can draw your arrows going clockwise. It doesn't change the problem at all. Okay. So there's my tangential speed. Keep in mind that the velocity always changes because the direction always changes as the object rotates in a circle. So it can have a constant speed, but its velocity cannot be constant because the directions keeps on changing because the velocity is a vector. All right. The next thing I want to draw is my t. Because it is attached to a string, this little m here that's on the table, there has to be some sort of tension in the string that's causing this particular mass m to orbit or to rotate in a circular motion. All right, so that's that for the little mass here on the surface. And the next I want to draw out is f of g for the hanging block. Here the hanging block's indicated with capital M. So instead of M1, M2, we're just going to use little m and big M. So here is the weight of big M, which is f of g. And this f of g is contributed to big M. Okay, keep that in mind. And then, well, what's holding it up? It says here the system stays in equilibrium. So there it's attached to the string that's attached to the little m. So there has to be a tension as well. And here I'd like to point out that if you read the problem correctly, it says what value or what is the value of m if it stays in equilibrium. Well, in order for the system to stay in equilibrium, the net force here on the hanging block has to be 0. So it indicates that the magnitude of tension here pointing upward must be equal to the magnitude of the weight of the hanging block. Otherwise, it will accelerate up or down, but we don't want that to happen. We want it to stay in equilibrium, okay? All right, let's go ahead and set up the physics for big M and little m. Here, I want to go ahead and set up for a big M first because the question asks you to derive a value of M, right? Capital M here in terms of all this stuff here on the left side in your answer choices. So you notice I underlined the phrase or the word equilibrium here because this is important. So to set up the physics for the hanging block, which is capital M, here I'm just going to set that the net force for capital M is 0. It's 0 because it's in equilibrium. Okay, in order for an object to stay in equilibrium, its acceleration must equal to 0. But for acceleration to equal to 0, you have to have at least two forces: one pointing up, one pointing down, or one pointing right, one pointing left. In this case, the hanging block is capital M. We will have a T that's pointing upward, but then we have the weight of the hanging block that's pointing downward. So those two must equal in magnitude, and if they equal in magnitude, the net force must equal to 0. So I want to keep the right side of the equal sign 0. However, if I look at the hanging block here, I have T pointing up, I have f of g pointing down. So what I'm going to do is I'm going to say T, which is pointing upward, minus f of g, which is pointing downward, must equal to 0. So in this case, to solve for m, I'm going to go ahead and move this f of g or negative f of g to the right side. I'm going to add that to 0. So again, moving the variable here changes sign. Negative f of g becomes positive f of g. But then we know f of g by definition is just mass times gravity. Well, which mass is it? Well, we're currently setting up the physics for capital M on the left side of this particular chart. Okay, so here we say that the tension is equal to big M times g, whatever big M is. But keep in mind, we're asked to derive an expression for capital M in terms of all these other variables. So when you get to here, you have to focus on what is being asked of you. It's asking us to find capital M. So to get rid of g, I would divide both sides by g, so we have m is equal to t over g. Well, all these answers have a g in it. It has a g there, has a g there, has, well, a g in the numerator, has a g in the denominator. So we know we're kind of close. What I don't see in all these answer choices is a capital T. Well, that should hopefully indicate and trigger that you need to do something with the capital T, okay? Well, I can now set up the physics part for the little m that's rotating in a circular motion along this frictionless table. Well, Well, what's causing this little m to rotate in a circle? It's this tension. In this case, the only force pointing towards the center of this circular motion is the tension in the string. Okay, I mean, it's frictionless. There's no friction and stuff like that. So I can say that the net force for a little m that's on the table is just T, because that is the only arrow that I see. Well, that arrow also represents your centripetal force. Well, but we know centripetal force is mass times V squared divided by R, or capital R in this case, because the diagram gives us capital R. Well, I don't know what T is on this side, but I know that the tension is the centripetal force for the little mass on the table. So now that I know what T is equal to, I can just do a quick substitution. Okay, so T is equal to mv squared over capital R. So wherever that is, I'm just going to replace out T. So T here is in the numerator, so I'm going to use parentheses. I'm going to say that T is equal to little m v squared divided by capital R divided by G. So here you have a fraction divided by a constant. Okay, so therefore anytime you have a fraction divided by a constant, you would just simplify it by multiplying, the two denominators. So in order to simplify a fraction divided by a constant, you just multiply the two denominators together. So therefore we have mv squared divided by r times g, and that is capital M. And this function here, mv squared over rg, resembles choice A. So I'm going to go ahead and say that the answer for this particular question is choice A. All right, I hope that helps. Stay nerdy, don't be whack.